Welcome to G Fun Facts Online. Today, we are stripping away the hype and looking directly into the silicon soul of a machine that might just redefine intelligence itself. We are talking about Hala Point. On April 17, 2024, a collaboration between Intel and Sandia National Laboratories resulted in a watershed moment for computing history. They unveiled the world's largest neuromorphic system, a machine designed not just to calculate, but to process information like a biological brain. This isn't a server farm taking up a football field. Hala Point packs 1.15 billion artificial neurons and 128 billion synapses into a chassis the size of a standard microwave oven. It is a glimpse into a future where computers are no longer energy-hungry number crunchers, but efficient, adaptive systems that learn in real time. To understand why Hala Point is such a big deal, we first need to look at the computer you are likely using right now. Whether it is a smartphone or a weather forecasting supercomputer, almost all modern machines are built on the von Neumann architecture. This design separates the processing unit, the CPU, from the memory, the RAM. To do anything, data has to be shuttled back and forth between these two components, billions of times per second. This constant movement creates a bottleneck, and, more importantly, it consumes a vast amount of electricity. Hala Point destroys this paradigm. It is neuromorphic, which literally means brain-shaped. In your brain, memory and processing are not separated. They happen in the same place, the neuron. Hala Point mimics this structure in silicon. Let's look at the specifications of this titan. It contains 1.15 billion neurons, which is roughly equivalent to the brain of a small owl or a capuchin monkey. For comparison, the previous generation system, Pohiki Springs, had only 100 million neurons. It has 128 billion synapses, the connections where learning physically resides. It is powered by 152 Intel Lohi 2 chips. And here is the statistic that shocks engineers. Despite capable of 20 quadrillion operations per second, the entire system consumes a maximum of 600 watts. That is about the same energy usage as a high-end residential clothes dryer. A standard supercomputer with equivalent processing power would require megawatts of electricity to run. The secret sauce behind this efficiency is the Intel Lohi 2 chip. Released in late 2021, this chip is fabricated using the Intel 4 process. Unlike a standard CPU, which has a few powerful cores, a single Lohi 2 chip contains 128 neuromorphic cores. These cores are not designed to execute lines of code sequentially. Instead, they simulate spiking neural networks, or SNNs. This is the critical difference. In a standard CPU, a global clock coordinates every action. If the clock ticks 3 billion times a second, the chip works 3 billion times a second, regardless of whether there is work to do. Lohi 2 is asynchronous. There is no global clock. Parts of the chip only wake up and consume power when there is data to process. If nothing is happening, it sits in near-zero power dormancy. This brings us to the concept of the spike. To understand Hala Point, you have to understand the difference between artificial neural networks, which run things like ChatGPT, and spiking neural networks, which run on Hala Point. Current AI uses artificial neural networks. These are mathematical abstractions where information is passed as continuous numerical values. Every neuron in a layer calculates a value and passes it to every neuron in the next layer. It is a dense, synchronous matrix multiplication. The flaw here is waste. Imagine an input that is a picture of a black sky with a single white star. A standard AI processes every single black pixel with the same intensity as the white star. Hala Point uses spiking neural networks. In this model, information is not a continuous number, it is a discrete event, a spike. A neuron is either silent or it fires. This creates sparsity. Neurons only fire when the electrical charge builds up past a threshold. If there is no change in the input, like the black pixels in the sky, the neurons stay silent and consume no energy. Furthermore, time matters. In standard AI, time is just a sequence of steps. In SNNs, the timing of the spike carries information. A burst of spikes coming closely together means something different than spikes arriving far apart. This event-based processing mimics the sparsity of the human brain, which never activates all 86 billion neurons at once. However, building a computer with 1.15 billion neurons is only half the battle. You cannot program Hala Point with C++ or Python in the traditional sense. You cannot write a for loop that iterates over a billion neurons. To solve this, Intel developed Lava, an open-source software framework. Lava is to neuromorphic computing what TensorFlow is to deep learning. It provides a layer of abstraction so researchers do not have to program individual electrical pulses. It is modular and composable, allowing developers to build independent processes, like a vision process or a motor control process, and connect them. Crucially, Lava includes a compiler that maps high-level behavior down to the binary instructions that configure the physical synapses on the chips. So, what is this machine actually used for? The system is deployed at Sandia National Laboratories, and they are not using it to run video games. The killer app for Hala Point might actually be physics, not just AI. Many physical processes, like the diffusion of gas or the movement of radiation through a shield, can be modeled as random walks. On a standard GPU, calculating millions of random paths is computationally expensive because of the memory bottleneck. On Hala Point, each walker can be represented by a spike moving through the neural mesh. The hardware structure physically maps to the problem. Sandia has demonstrated that for these diffusion problems, neuromorphic chips can be 10 times faster and 100 times more energy efficient than conventional processors. Another major application is optimization. Consider the problem of routing 10,000 delivery trucks to minimize fuel or scheduling 500 trains on a railway network. Hala Point solves these using constraint satisfaction. The neural network settles into a low-energy state that represents the optimal solution, converging on the answer much faster than a brute force search. Perhaps most exciting is the potential for continuous learning. Current AI models like large language models are frozen after training. To learn a new fact, they must be retrained at great cost. Because the synapses on the Loihi 2 chips are programmable and plastic, Hala Point can update its knowledge in real time without forgetting what it already knows. This is vital for autonomous drones that need to adapt to wind damage mid-flight, or smart grids that need to balance power loads instantly. It is inevitable to compare Hala Point to other systems. IBM had True North in 2014, but it was rigid and could not learn on the chip. The University of Manchester has Spinnaker, which uses standard ARM processors to simulate neurons via software, making it flexible but less efficient. And of course, there are NVIDIA GPUs. For dense matrix multiplication, like training a massive transformer model, GPUs are still king. They are optimized for brute force. But for sparse data, such as video surveillance where nothing moves for hours, or complex graph optimization, Hala Point destroys the GPU in efficiency, offering up to 50 times speedups and 100 times energy reduction for specific workloads. Ultimately, the unveiling of Hala Point reignites the discussion about artificial general intelligence, or AGI. Current AI is essentially super advanced statistics. Neuromorphic proponents argue that to achieve true reasoning, we need to copy the substrate of intelligence, the brain. The human brain consumes about 20 watts. A supercomputer simulating a brain currently consumes megawatts. We cannot build a GI if it requires a nuclear power plant to run. Hala Point's extreme efficiency is a necessary step toward intelligence that can exist in the real world. While 1.15 billion neurons is only about 1% of the human brain's scale, Hala Point proves that the architecture scales. Connecting 1,000 chips worked. Connecting 10,000 is an engineering challenge, not a scientific impossibility. Hala Point validates a biological truth that intelligence is efficient, sparse, and interconnected. We are moving away from the era of brute force computing, where we solve problems by throwing more electricity at them, and into the era of elegant computing. As researchers at Sandia begin to write the first brain-scale programs for this machine, we may soon find that the best way to build a smarter computer was sitting inside our heads all along.